So next we'll discuss some problems that are in NP-complete, and we'll prove one of the problem as NP-complete problem. So we said earlier that to prove a problem in NP-complete, we will take an existing problem and reduce it to a new problem. But if we keep going like that, let's say new problem is Z, we prove from existing problem Y. New problem is Y, we prove from existing problem X. So there has to be a first problem which has to be proved hard. So one of the first problem that was proved hard vigorously is the problem of satisfiability. So what is the satisfiability problem? Is the problem of Boolean satisfiability of a formula. That is, if we are given a formula, Boolean formula, where the literals can take Boolean value of true or false, is this formula satisfiable? That is, for three variables we have here x1, x2, x3. Is there an assignment that can make this formula true? For example, if we assign 0, 0, 0, will it be evaluated to true? No. So we will get 0 and 1, this will be evaluated to 1, but 0, 0, this will be evaluated to 0. So total formula will be evaluated to 0 only. The question we are asking, is there an assignment of the Boolean values that will make this formula true? Okay, so output is we have to give the assignment, and for decision problem we have to say yes or no. Is this formula satisfiable or not satisfiable? Okay. So for example, here if I take x1 as true and if I take x2 as true, then both the clauses become true and it will be satisfiable, because x1 true, x1 true, fine. x3 does not matter. Okay. So that was the first problem proved to be NP-complete. That also we call as Cook's theorem, who proved that Boolean satisfiability problem or SAT is a NP-complete problem. Okay. And any other new problem, actually we reduce to this problem or a related problem to prove that is a NP-complete problem. So like this we generally prove SAT. Already we know NP-complete. So we reduce SAT to 3 SAT and prove that 3 SAT is NP-complete. Then we reduce 3 SAT to Clique to prove that Clique problem is NP-complete. Then we reduce Clique to Vertex cover to prove Vertex cover is NP-complete. Then we can reduce Vertex cover to subset sum to prove that subset sum is NP-complete. Like this chain of hardness or hardness flow through this reduction. Okay. So look at one example where we'll assume that 3 SAT problem is NP-complete and we'll reduce it to Clique problem. That way we'll prove that Clique is also NP-complete. So once we prove a problem to be NP-complete, we can always reuse it to prove any other problem as NP-complete. So it forms a network. Okay. So by formal definition of NP-complete problem, as I told earlier, two conditions. First, suppose problem B we are trying to prove. B has to be NP, belongs to NP, that is solution can be verified efficiently. If you are given a solution, you can verify efficiently. And second, we have to take a non-NP-complete problem, let's say A, and we have to reduce it to B. Okay. And the interpretation is B will be at least as hard as A. Okay. Since A is already hard, B also must be hard. Okay. And strategy, as I told, we start from a known NP-complete problem and we reduce it to a new problem. So the example, as I told, we'll discuss 3 set to Clique. So first let us understand the problems. What is 3 set? So 3 set is a variation of satisfiability problem, it's Boolean satisfiability problem only. Only difference is here the Boolean formula is in conjunctive normal form, CNF, that is AND of odd terms, right? And where every clause has exactly 3 literals. So this we call as clause. So we have 2 clauses and inside every clause we have literals. So we have 3 literals in every clause. So this is called 3 set problem. And the question we are asking, is this formula satisfiable? Is there an assignment of true false values that will satisfy the formula? Okay. So this is the 3 set problem. Next look at the Clique problem. Clique problem is a graph problem. So Clique is a set of vertices where every pair is connected to each other. So if I take 2 vertices, if we connect them, this is a clique. If I take 3 vertices, each vertex, that is every pair of vertices is connected. So this is connected, this is connected, this is connected. So this is a clique of size 2. If I take 4 vertices, all pair must be connected. So this is still not clique. I need 2 more edges. This is a clique of size 4, right? So in a graph, we can find the clique. Like for this graph, we can take different subsets. So if I take these 4 vertices, is this a clique? It is not a clique because this edge is not present. Okay, so it's not a clique. If I take these 3 vertices, is it a clique? Yes, it is a clique because every pair of vertices is connected. But is it the maximal clique? That is, these 3 vertices, can it be part of a larger clique? Yes, it can be part of a larger clique. So this is not a maximal clique because these 3 vertices, I can take the 4th vertex and this is part of a larger clique of size 4. It was size 3. When I take these 3 vertices, is it a clique? Yes. Is it a maximal clique? Yes, because these 3 vertices cannot be part of any larger clique. Right? Fine. So in the decision version of the problem, we ask, given a graph G and an integer K, does G contain a clique of size K? So we can ask, does this graph contain a clique of size 2? Yes. Does this graph contains a clique of size 3? Yes. Does this graph contain a clique of size 4? Yes. So that is the question we ask. If we ask 5, no, it does not contain a clique of size 5. So optimization version of the problem asks you to find the maximal clique. Okay. Decision version we are asking, given some K value, say K equals to 4, is there a clique of size 4? Okay, so answer is either yes or no, like previously we have seen decision version of the problem, yes or no. Fine. So we want to prove this problem is NP complete. So what we have to do? So as we said earlier, so before going to reduction, first is we have to prove that it is NP. To prove it is in NP, we have to show that given a solution, it is verifiable in polynomial time. Right? So can we do that? Okay, Let's remove this. So yes, that we can do easily. Like if I take from this graph and I can give a click from it, I can give this 4 vertices and all connected edges, and we can ask, is it size 4 click? Yes, no. How will verify? So we can verify for every vertex, is it connected to all other vertices or not. So we can take each vertex and verify is it connected to all other vertices or not. So yes, this is a click, and we can verify it in polynomial time. Right? Just every vertex I have to check is it connected to other vertices or not. Yes. So it is verifiable in polynomial time. That means clicks belongs to NP. That is the first thing. Next thing that we need to prove is clique is hard. So how will prove clique is hard? To prove that, we said we'll take the 3-set problem and we will reduce it to clique problem. So we'll take instance of 3-set problem and reduce to clique problem. Let's see. So how we'll reduce it? Simply, for the given Boolean formula, we'll convert into a graph problem by creating node. So each literal will create one node. Okay? And each clause will create a group of nodes. And then we'll add edges. When we'll connect edges, first thing is we'll connect two nodes only if their literals are not conflicting. So if there is a x1 node and there is a not x1 node, here we cannot add edge because these are conflicting. Okay, but I can connect x1 to x2, I can connect x1 to x1 also. So only if two nodes are complementary or conflicting, will not add edges. Otherwise, every node will connect to every other node. Except one more condition, within a group will not add any edge. So if we have 3 nodes, let's say these 3 in a group, within this group I will not add edges. We will connect it to other vertices. Okay, fine. So let's look at an example. So in this example you can see what is the formula. So we have total 3 clauses, right? So the formula is we have x1 or not x2 or not x3 and not x1 or x2 or x3 and x1 or x2 or x3. Okay, so this is the 3-set formula. We are asking, is it satisfiable or not? Now how do we convert it? For every literal we'll create a node. So you can see total 9 literals are there, we have created 9 nodes. Then we start connecting these. As I said, this belongs to same group, so there will be no edges among these vertices. And then we'll try to connect x1 to all other nodes outside the group. So can we connect x1 and not x1? No, because these are complementing. Can we connect x1 and x2? Yes, so we draw edge. Can we connect x1, x3? Yes, so we draw an edge. x1, x3 again, x1, x2, x1, x1. So like that, from every vertex we have drawn edges, right? So from not x2, we cannot connect to x2. So not x2, so we connected not x2 to not x1, x3, x1, x3. So like that, this 3-set problem is converted into a graph. Fine. Now, how clique will be related here? Now the question we'll ask here, so in the original 3 formula we had how many clauses? We had 3 clauses. Okay. Question we are asking, is it satisfiable? Okay. So answer can be yes, answer can be no. Now in the graph, the question will ask, does the graph contains a clique of size 3? Okay. And if the answer is yes, if the graph contains a clique of size 3, then answer for the previous problem is also yes. That is yes, this formula is satisfiable. And if the answer is no, there is no clique of size 3, then this answer also will be no, the formula is not satisfiable. Okay. So let's see, do we have a clique of size 3? Yes, I can take suppose this one, not x2, x3, x3. So these 3 vertices are connected. So this is a clique of size 3. Yes, it contains clique of size 3. Then yes, this formula is satisfiable. For what value? So we can take the clique, whatever the nodes are there. What are the nodes? We have taken not x2, and we can take x3, and the other one also x3. So only actually 2 unique values, unique literals, and we'll set it to 1. And for this, the formula also will be satisfiable. You can check it. Not x2 is 1, x3 is 1. So not x2 is 1 means here this is 1. So this total thing will become 1. In this clause, x3 is 1. So total clause will become 1. And this third clause, again, x3 is 1. Total clause will become 1. So every clause is 1. So the formula also will be evaluated to 1, right? And if you think why, so that way, first of all, we converted the formula into a graph, and then we solve a graph problem. And whenever the graph problem is solved, there is a solution. Clique also has a solution. And that way I say that the 3-set problem is reduced to clique problem, right? That is, if clique can be solved efficiently, then 3-set also can be solved efficiently. Okay. And why that is true, if we discuss a little bit about it. So when we say clique of size number of clauses, in that case, we know that within the clause there are no edges, right? So if you have to pick 3 vertices, that must be from 3 different clauses, first thing. Next, if I am picking from 3 different clauses means, another question we put that it should not be complementary. I cannot connect complementary. So if I pick here not x2, I cannot put x2 here. So at the same time, it cannot be both 0 and 1, right? So we are making sure if not x2 is picked, we will not pick x2. So same way, whatever vertices we are picking up for the clique, we can uniquely assign them 1, because there is no contradiction, no complement present in it. And that means every clause has at least one literal as 1. So every clause become true, the formula also become true. So this is the reduction of 3-set problem into the clique problem. Okay. So yeah, so reduce 3-set to clique. We know that 3-set is a NP-complete or hard. So clique also must be a hard problem. Actually should be say NP hard. And clique is already we have seen first case, it is verifiable NP. Second case we are seeing it is as hard as 3-set. As both are true, then we can say that Clique is also belongs to NP-complete. Fine. So again, that hardness is transferred through reduction. So this is the way of proving the problem, that a problem is NP-complete. Fine. So same way there are other problems. As I have shown earlier, you can reduce one problem to another. Like there are graph problems like vertex cover, Hamiltonian cycle, scheduling problems, or code generation problem, which is register allocation problem. Ultimately it's a graph coloring problem. Okay. So these problems also can be one problem reduced from existing problem to show that all these problems are NP-complete. Fine. Okay. And these problems are different area you will find, like in graph theory you will find optimization, scheduling, compiler design. These hard problems are NP-complete problems you will be finding. Okay. So this arises in many real world applications. Fine. So same way we can show that Clique can be reduced to vertex cover. This is another problem where in vertex cover we ask, is there set of k vertices that cover all edges? So I'll just briefly tell it. Suppose, yeah. So here we'll ask, the question is that, let's take this. Is there a vertex cover? What is a vertex cover? Vertex cover means we have to take certain vertices that will cover all the edges. So you can think like, can we put people in certain positions such that all these hallways are covered or guarded? Like if I put a person here, these two will be guarded, right? If I put a person here, these two will be guarded. And if I put a person here, these two edges will be guarded. That way, how many vertices we need? We need 3 vertices to cover all the edges, right? Yeah, to cover all the edges. So this is a vertex cover of size 3. So similarly ask, given a graph, is there a vertex cover of size k? Right, that is the question we ask, and we can show that this problem can be proved to be NP-complete. Again, how will prove? First thing, if I give any cover, I can check is it really a vertex cover or not. Correct? Yes or no? So I just need to check if I give the vertices, is it covering all the edges? So that we can verify in polynomial time, and then the problem belongs to NP. Second thing, we can take the Clique problem and we can reduce it to vertex cover problem. And that way we will prove that vertex cover is as hard as Clique. So because of these two, then we can infer that vertex cover is NP-complete. Right? Same approach. Fine. So like that, all these problems we can prove. Like I said earlier, Clique, SAT can be reduced to Clique, Clique can be reduced to vertex cover can be reduced to subset sum. Fine. So in conclusion, what we learned here is that there are some problems that are efficiently solvable, then there are some problems that are hard, but solution can be verified. That is NP problem, and then there is NP-complete problems that are the hardest problem in NP, as hard as any other problem in NP, right? And the tool to prove this problem is NP hard, and in turns, as it is NP plus NP hard, it is NP complete. The tool we use the reduction, and we use the Cook's theorem, where he proved that SAT is a NP complete problem, and we use reduction from SAT to a new problem to prove the other set of problems that are NP complete. Okay. And as we said, we are doing reduction, that is taken a problem, A is reduced to B, B is reduced to C, C is reduced to D. If any problem is solved efficiently here, if D has an efficient solution, that means as C can be converted to D, C must also have an efficient solution. Same way as B can be converted to C or reduced to C, if C has an efficient solution, B also must have an efficient solution. And as A can be reduced to B, so if B has an efficient solution, A has an efficient solution. So that is, if any NP complete problem is solved efficiently, all NP complete problem will be solved efficiently, and there will be no problem remaining that is not in P, right? So all NP problem will become also P problem, and P will become equals to NP. Okay.